Hello everyone, welcome to this webinar on modeling thermoelectric devices using COMSOL Multiphysics. My name is Lexi and I'm a technical marketing engineer working out of our Burlington, Massachusetts office. Our speakers today are my colleagues Nicholas Uk and Yosuke Mizuyama. Yosuke is an applications engineer with a PhD in applied math for the finite element method, and Nicholas received his PhD from the University Joseph Fourier in Grenoble, France, and he leads the development of the heat transfer physics interfaces in the COMSOL software. After their presentation, we'll answer some questions from the audience, and you can ask questions by typing them into the text field in your webinar controls. They'll be sent to us from there, and you can do that at any time during the presentation, so we'll answer as many as we can at the end, but you don't need to wait for the Q&A session to do that. So you can go ahead to the next slide, Nicholas. This is our agenda for today. I will begin with an introduction to simulation and more specifically to modeling and app design with COMSOL Multiphysics. And then Nicholas and Yosuke will discuss some specifics of how to use COMSOL for studying heat transfer, electric currents, the behavior of thermoelectric devices. And as I mentioned at the end, we'll have the Q&A session and you can submit your questions at any time. You don't have to wait for that to start. And then we'll wrap up with some information on how you can learn more about COMSOL. So you can go ahead to the next slide. And first, we're going to take a quick look at why you'd want to use simulation in the first place. If you're going to create a new product or process, you first want to make sure you get the concepts right. And multiphysics simulation gives valuable insight into how your product will perform in the real world. And with that kind of understanding comes innovation. And simulation also benefits the design and optimization stages. It reduces the time and money spent on prototypes. And integrating modeling with manufacturing and quality assurance means that you end up with a product that's better understood and better characterized. So working with testing and manufacturing, simulations allow you to test and verify the quality of your device or process before moving to production. So you can go ahead to the next slide, Nicholas. All right. COMSOL is a multiphysics simulation and application design environment where all the steps of a simulation are integrated into a single user interface. From the initial setup to solvers to post-processing to building an app from your COMSOL model. And COMSOL allows you to couple together physical effects the way they would be in the real world. These are what we refer to as multiphysics. And by that we mean two or more physical effects that interact with each other, and there's no limit on the number of physics that you can include in your model. So if you take a look at the diagram on the right, these are some examples of the different physics you might include in a single model, and you can couple those together in the software. You can use the built-in physics interfaces available with COMSOL. You can also define your own custom physics if you need to. So there's a lot of flexibility here depending on what you want to do. And then there are also benefits to staying in the same environment for single physics simulations. That allows you to use the same workflow no matter what your task is. So you can go ahead to the next slide. And this is our complete product suite. We have add-on products that can be combined with the COMSOL Multiphysics core package. And that enables the simulation of specific physics phenomena across a range of application areas. And as I said, these can all be combined with each other. So we have modules for electrical, fluid, mechanical, chemical applications. We have several multi-purpose modules, and then there are tools also for interfacing with external software platforms. And as I mentioned, each of these modules contains predefined physics interfaces, but you can also define your own custom physics and equations depending on what you need. You can go ahead to the next slide. And this is the COMSOL desktop. So this is the interface that you'll see when you open up the software. It's pretty straightforward to use. All the modeling steps are recorded, and these can be modified later on as needed. And that happens in the window shown on the left here, referred to as the Model Builder. That's where you input or select custom settings. These are done in the Settings window, which is right now is below the Model Builder. And then visualization and results are shown in the graphics window on the right. And clicking on a specific node in the Model Builder lets you view all the relevant parameters and equations in the settings window. And it's also possible to evaluate and couple several model components in the same file. And then accessible from the Home toolbar, we provide application libraries, and these have many helpful example models and applications. This is a great place to see how you might model something in COMSOL, and that can help you in your own work. You can start there. That's a good starting point. There are heat transfer and thermoelectric examples included in those libraries. And then if you take a look in the upper left corner of the COMSOL desktop, this screenshot, there's a button that says Application Builder, and that gives you access to the Application Builder portion of the COMSOL desktop, and that's where you would create a customized app for another user. So if you go to the next slide, this is the COMSOL desktop showing the Application Builder instead of the Model Builder, and then there's, with a click of a button, you can easily switch between them. And the Application Builder is where you create that app ready, so you could share that with a colleague or a customer. You can create a simulation app from your COMSOL model. The end user doesn't need to know how to use COMSOL in order to use the app you design for them. This is what makes it really powerful. They can still benefit from the modeling capabilities for product design, but they don't need to know everything that went into the simulation itself. And then you can choose what the end user has access to and what they can edit as inputs. So anything that's parameterized in your model can become an input in the app, and the value can then be changed by the end user. So the Application Builder features a form editor. This is what we're looking at in the background screenshot, and that allows you to customize the app's user interface. This is where you add input fields, graphics, tables, other features relevant to your model. And then the app shown in the foreground here is an example of the finished product. This is what the end user would see. And this one is based on a model of a thermoelectric cooler. The Application Builder also contains a method editor, and that allows you to include programming and further customize the simulation app designed from your COMSOL model. So once again, a lot of flexibility here if you want to use it. If you go on to the next slide, the next obvious question once you've created an app is how do you run it and how do you share it? You can open and run an app from COMSOL itself. You can also make it possible for other app users who don't actually have COMSOL installed on their machines to run it as well. And for that, you want the COMSOL server. And then an app user can install a COMSOL client or can actually use a web browser to run an application hosted on the server. That makes the app accessible worldwide. Any updates to the app are immediately available to the user. And on this slide, you can see how that same app for the thermoelectric cooler model would appear run in the COMSOL client. And that is it for my introductions. Thank you very much for your attention. I'm going to turn it over to Nicholas now.
Thank you very much, Lexi, for this introduction. We'll continue this webinar with some details about heat transfer and electric current, especially in COMSOL Multiphysics. But the first step to go to a thermoelectric effect that we will reach soon in this presentation. So heat transfer in solid can be modeled, and we will focus on the classical cases where all the heat in the solid is described by heat transfer by conduction, and around the solid we may have a fluid, and due to the fluid some convective cooling. The convective cooling effects can be modeled using some heat transfer coefficient just by defining a flux condition on the boundaries of a solid, or we can also model the flow going through the solid and all the non-isothermal flow with flow velocity, pressure, and temperature to get an accurate description of the heat exchange between this fluid and the solid. And also, while we are talking about the heat transfer to boundaries of a solid, we may have a surface-to-surface radiation between one solid and the other solids, or between the solid's boundary and the surroundings, as well as we may have heat transfer in participating media in the solid or outside the solids. And the interesting point to focus on is the way it's described. Of course, we don't need to know everything about the theory, but I just recall the equation we are solving here because they are of interest when we go to thermoelectrics. So the heat transfer by conduction that occur in the solids occur indeed in any material, and all the material can be characterized by a thermal conductivity that is used to define the heat flux by conduction from the Fourier law. So here we have an energy balance equation, which has a storage term with the time derivative of a temperature, and a divergence of a heat flux, which is coming from its definition is coming from a 4 yellow. And we also have a heat source, which is noted Q here. And the heat source may be defined by the user or defined from another physics. And we will see that in the case we are looking at today, thermoelectricity, the heat source play an interesting role. Okay, and to go to thermoelectrics, we also have to speak about electric current. So the modeling of electric current is based on the current conservation, and we may have a different boundary condition in solids where electric currents occur. The most common are just current condition or potential electric potential conditions, but there are also more advanced conditions like electric shielding, floating potential, etc. that can be used in models and are available in COMSOL Multiphysics through a dedicated features. And here also I'm recalling the corresponding equation. So the current conservation equation is divergence of J is equal to 0, where J is defined from the Ohm laws. And to define J, we need the electrical conductivity, sigma. So again, that's something which is a material property and which is defined for any conductive material. And when we have defined the heat conduction and the current conservation in solids, we can go to the next step, which is the Joule heating. Joule heating is something that occurs as soon as you have electromagnetic losses. Then you can experience a rise in temperature, and this is due to a heat source coming from the electric current. So the heat source can be is given by an equation again. It's J dot E, the electric current dot the electric field. This is an irreversible process, so it means that what is lost, the conversion between electric current to heat, is not something you can revert. And which is interesting to note also is that there is what we call a two-way coupling, because in one way the electric current influences the temperature field, but on the other way the electrical conductivity is also temperature dependent. So in most of the cases it's interesting to define the electrical conductivity as a function of a temperature. So now we have all the ingredients to address the thermoelectric effects. We'll see that it's something that comes in top of heat transfer, electric current, and Joule heating. So what are the thermoelectric effects? This is a reversible conversion of thermal energy in electrical energy, or of electrical energy in thermal energy. There are some effects that are known as Seebeck Effect, Peltier Effect, and Thomson Effect, which are all included in what is called Thermoelectric Effect. And for example, on the right, we have an illustration of a very simple model where we observe a temperature drop due to electric current, and so this is called the Peltier effect. And so let's go back on the different Seebeck, Peltier, and Thomson effect that has been named after the scientists who discovered them. So the Seebeck effect has been discovered when it was noticed that when two different conductor wires, one in blue here and another one here, are connected together, and when a difference of temperature is imposed between the junction, then tension raise is observed in the loop, and it has been shown that this temperature, this voltage is proportional to the temperature difference. So there is a Seebeck coefficient, noted S here, that links the temperature change with the voltage change in the Seebeck effect. And kind of, I said that these effects are reversible, so the reverse of a Seebeck can be seen as the Peltier effect. If you if you prescribe a potential difference in the same loop, then you will see that at the junction you will have a heat flux, one positive and one negative heat flux, depending on the junction, and this is an effect which is very interesting for the cooling and, for example, for the portative fridges or the cooling device that require high accuracy or that require to be very quiet, for example. And after these two discoveries, Thomson effect was eventually shown, and it was shown that the thermoelectric effects are not occurring only at the junction, but they are also occurring in the thermoelectric devices along all the wires. So the Thomson effects describe a heat source occurring in thermoelectric material, which is proportional to J, the electric current, and the temperature gradient in the wires here. And the thermoelectric effects gathered all together are related by some expressions that introduce some coefficients, the S coefficient here, from which we can define the P coefficient and the mu coefficients. And thanks to these definitions, we can redefine the heat flux and the electric current so that we account for the thermoelectric effect. So you remember that I introduced the heat flux from the Fourier law, and here we can see that the heat flux has been redefined to account for the P, the Peltier coefficient, time J, and the electric current also has a contribution from the Ohm law, of course, and another coming from the Seebeck effect times grad of T, which describe the thermoelectric effects. So before I go forward in the demo, we'll have one question for you, one poll question. So the question is, what kind of simulation are you currently doing? Are you doing no simulation? Are you doing heat transfer simulation, electric currents, Joule heating, and thermoelectric effects? You can select multiple questions. You should have a poll question that will show on your screen. So you can click one or multiple answer. Okay, thanks for answering the poll question. I guess you got the result. I don't have a feedback about the result now, so I will not comment them right now. I'll go back to the presentation. So of course, when you are using COMSOL Multiphysics, you don't need to know and to be able to write the theory for thermoelectric effects. I was just introducing the difference between simple heat effects and electric effects compared to thermoelectric effects. But now that we are aware of that, that's enough to work with COMSOL Multiphysics interface. So in COMSOL Multiphysics, you have a predefined interface which is called thermoelectric effects. And if you select that, you get, of course, all the equations set up, and you don't you don't need to know more than what are the thermal conductivity, electrical conductivity, and Seebeck coefficients. Typically, that's it. So when you select this interface, you get two what we call physics interface. One is called heat transfer in solid. Another one is called electric current, and you have a multiphysics node that includes the thermoelectric effect. So this multiphysics node is making sure that electric current interface is solving the equation corresponding to the thermoelectric effect, as well as the heat transfer in solid equation is accounting for the Peltier effect, for example. So when you take this multiphysics coupling, everything is defined for you. And what I would like to do now is to show this in COMSOL Multiphysics interface in a live demo, and to build one of the simplest model you can imagine. So this is a thermoelectric element made of two thermoelectric materials, one of P-type and one of N-type. So they are connected through aluminum layers here, and outside we have alumina, which insulates from electric point of view the device. For the electric side, we'll set a ground condition on this part, an electrical potential on this part, and we expect to have a current going through the device and drive this end here. And from the heat condition, we'll just put a temperature condition on the bottom side, and we expect to have the cold side on the top, and we'll see how well the device performs. So what we'll get as an output is a typical output will be a temperature graph where, depending on the direction of the current or the potential we set on the here, we'll get either a heating or cooling effect. So now I go to COMSOL Multiphysics. This is COMSOL Multiphysics interface. When you start it, you have access to a wizard. In this wizard, you have to answer a couple of questions, like the space dimension. So here we want to work on the 3D geometry. Then you have access to a list of physics sorted by different folders. So here, today we are looking into heat transfer application, where you can find thermoelectric effect. So anytime you select a physics, you have a description of what it does. And if you add it to the model, then you have a different components. So we have a heat part, the electric current part, and the multiphysics coupling. The multiphysics coupling, it's interesting to note that it's the thermoelectric part and also the electromagnetic heat source, because, as I said, as soon as you have electromagnetic losses, you have some heat source associated to that, so you cannot separate them. And when you have selected the physics, you can also select the kind of study you want to perform. Today we'll keep it as simple as possible with a stationary study. So again, you have a description of what it's doing. And when we are ready, we just click done here. So what we have to do to build the model and to solve it is to first create a geometry. To create the geometry, we'll just get it from something I prepared for the webinar. So instead of using all the primitives, I will just go there and insert a sequence. I have a model which is contains the geometry already, a file here. So I open it. I load the corresponding geometry sequence. So you can see that, you know, this geometry is made of blocks, and I can check what it is here. The interesting thing is that this geometry is parameterized. Here I have different parameters: the leg depth, height, width, the distance between legs, the copper thickness, the alumina thickness. So if I, for example, if I want a thicker alumina, I just change my parameter here. I go back to the geometry, I build it again, and you can see that, okay, you have a different geometry. So the geometry is ready. The next step is to define the material properties. So for that, I will add materials here. And I have access to different material. I'll go in the built-in for most of them. I will select the alumina, and I add it to the component. So by default, everything will be made of alumina after that. The next step is to add copper. I select copper, and I add it to component. And I will select the domain where I want to define copper. So I have 3 domains, this one, this layer, and there is also one layer here. So this is made of copper. And finally, I want to define the thermoelectric material, which is another place here. It's called thermoelectric. I have a bismuth reed, which I add to the component, and I will select this part, and I will call this material P-type. and by opposition of the next one that I will add. So I add another one, and I call it N-type. And the N-type will be modeled as a material with an opposite Seebeck coefficient. So instead of having S, I will have minus S. And so what I'm doing here, I'm editing the predefined material property to get an opposite sign on the Seebeck coefficient, but I keep the rest as it is. For example, Seebeck coefficient is defined as a function of the temperature, and this is something that I want to keep, so I keep it like that. And now that the material are defined, I forgot to select the domain. I realize, so I can do a check. Here I have alumina on the top and bottom layers, copper, and the P-type and the N-type. So now my material are defined, and I can go to the physics. So for heat transfer, I said that I will do it very simple. I just add a temperature condition on the bottom. So I select here the temperature condition. I select my phase, and I prescribe the temperature, which by default is 20 degrees Celsius or 293.15 Kelvin, which is exactly the same. And that's all for the heat transfer. Of course, I have by default, the heat transfer in solid equation, which is solved in the domain, and we will account for conduction. And thanks to this thermoelectric effect node, it will also account for thermoelectric effects. And I will solve it together with electric currents. And for electric currents, I don't want to solve electric current in the insulator, so I remove them from the selection. And I will just add a ground condition to define zero potential here, and I will define electric potential on this side. So the electric potential requires a user input. Which potential do I want to set? And I can type a value, of course, or I can also type the name of a parameter. Here it's V0. And if I go back to the parameters here, I can say, okay, I have a new parameter. It's V0, and it's equal to 0.1 volts. And it's called the input potential, for example. Okay, and if I go back here, okay, now the electric potential is recognized, and it will take the value. So typically that's it. I'm trying to build a Peltier effect with a current going through a device, and I expect to have some cooling or heating on this side. And I also see from the model that the Joule electromagnetic heat source, the Joule effect, will be taken into account. So now the question is, what temperature will I get in this configuration? And for that, I have to solve the problem. I click compute. Okay, it takes, oops, I forgot something. Yes, I forgot something. What I forgot is, if we go in the thermoelectric effect, I keep it active on the copper, which is not a thermoelectric material, so I haven't defined a Seebeck coefficient for this material, and I just forgot to deactivate the thermoelectric effect on the copper. So now the thermoelectric effect is only applicable, applied on the two thermoelectric parts. So I can solve it once more. And I should get a temperature profile. So now I have a temperature profile. So I have a column map. So the temperature shown here, the value is given by this column map. So the dark red represents the cold parts. So the temperature is given in Kelvin. If you are more familiar with another unit, you can go in the plot and change, okay, to something else, Fahrenheit, Celsius degree. Let's take Celsius degree and refresh the plot. So you can see that here the minimum temperature is about minus 40. So we have a nice cooling occurring here. And of course, depending on the current, depending on the geometrical configuration, you can get better or worse cooling effects. So that's typically what you want to do with this kind of model. You want to change the parameter and play with it. I hope that the quick setup here convince you that it's quite easy as soon as you are familiar with simulation and thermoelectric effects to build a model and to get a result within minutes. But as Lexi introduced in the beginning of his presentation, maybe that you want to deploy this kind of simulation and let people who are really not familiar with simulation and thermoelectric effects to do some tests. So in this case, what you would like is to build a simple app to let people change the parameters and to run simulation. So that's something we can do very quickly, very easily. I click this application builder button, and when I do that, I switch to a different workspace here to build the application, and I can edit forms, so I can create a new form, and I have a kind of wizard here that asks me, okay, what do I want to give access to in my model? And for example, I can let the user change the leg height here. I can let the user to change the input potential. What do I want to show as graphic? Okay, I want to show the temperature plot, and what kind of control do I want to give? I want to add a button to compute. I can name my form to something more interesting than form 1. If it's a simple thermoelectric cooler, maybe we want to call it thermoelectric cooler, and I validate. And as soon as I do that, I get here a sketch of my app where I can move a button around, but I can maybe enlarge the graphic windows like this. I can do a lot of things like moving the parts to. Oops, I forgot part of them. Better to select all of them at once and move like this. Okay, I can arrange my layout, and okay, when you are fine with it, you can just test your application. And what it's doing is just taking the user input from the model and putting them in a dedicated application, so that you just give access to the leg height, for example. You don't want 1.5 millimeter, but 3 millimeters, and then the user can just compute. So it cannot change the boundary condition, it cannot change the physics, it cannot change the coupling. It just can, run a simulation and get a result. And okay, here, what's happened if you put a strong input potential, you compute again, and your application is just giving the feedback to you. So yeah, in a few minutes we have been able to build an app. So here we see that it's interesting. If we put a high potential here, what we see is that we have a heating effect, a strong heating effect. That's the Joule heating, which is now dominating over the Peltier effect. So it means that if we put more power in our simple thermoelectric cooler, then we get less effect, just because the range of voltage is too high now. So I was saying that in a few minutes we have been able to build a model in COMSOL Multiphysics based on the predefined interface for thermoelectric effect. And from a model, also in a few minutes, you can build a dedicated app, and immediately you get some results like that. Of course, you can do much better than that. You can, keep working on the app. So the simple app I shown, and if you work, you parameterize the geometry, you work on the outputs you want to provide, the kind of study you are performing, then you get something really more advanced. And now Yosuke will show us what kind of finished result you can get by working more than I did on this kind of models.
Thank you, Nico. This is Yosuke. I'm going to present two simulations today. The first one is an app that was created by the application builder. This app can be used to design a standalone TEC device. The second one is an application model that is more practical and is almost ready to use for a complete set of TEC systems that includes a heat source and heat sink. Let me show you the first simulation. This app model has a rectangular standalone TEC device having 10 pairs of TEC elements. You can change the TEC length, width, height, element cross-section, pitch, electrode thickness, and ceramic thickness. You can also change the material from the selection menu like this. We have a lead telluride here. And note that in this app, that hot side temperature is fixed to currently 50 degrees C. With this app, it will take about 7 minutes to finish. So I ran this app earlier and got the solution already. Let's take a look at the computational results. The first result is a temperature distribution with no heat load. You can see the top is the cold side, and the bottom is a hot side, and the temperature difference is about 74 Kelvin. Next result is the result of a heat load sweep. Then cold side temperature changes, so is the temperature difference. This plot is one of the common characterization plots for TECs, which is the temperature difference between the hot side and cold side versus the heat that is removed from the cold side. This result plot tells you that the maximum cooling performance is achieved when the temperature difference is 0, which is an ideal case. And this TEC device can remove 2.6 watt heat as indicated here. So if you extend this line and it goes to 2.6 watt at the delta T is 0. In practice, there is no ideal heat sink, so there is always some temperature difference. So the achievable heat removal will be less than 2.6 watts, but we can still refer to this number as an index indicating the cooling capability. Keep in mind that after this up, I will show you another example model that has a real heat sink. Next one is we sweep the injection current with no heat load. This result plot is the temperature difference versus injected current. This curve shows that the more current you inject, the more you can cool the cold side. However, note that the cooling effect saturates at a certain point here, where the Joule heat becomes overwhelming. After this point, the performance of this TEC device will degrade. The last one is a parametric study sweeping several parameters and compares the coefficient of performance for some different situations. The coefficient of performance is defined as the removed heat divided by the consumed electric power. Remember that TECs cool something but also heat something simultaneously. If this number is 1, the TEC removes a certain amount of heat on the cold side by using the same amount of electric power. This also means that the total waste heat is twice the heat load. If this number is smaller than 1, the TEC can still cool, but it generates more heat than the heat load. So this plot gives you an idea about how efficient your TECs are in terms of economy. There are 3 lines here in this plot corresponding to 3 different types of heatsink. This blue one is a good one. Green one is poor performance. Red one is poor performance. The blue one is the smallest, gives the smallest delta T, which means that this heatsink can cool the hot side better than the other 2. The best efficiency of 1.64 is achieved at the normalized injection current of 0.25. This is it for this simulation. We have a poll question here. Let's see.
Yeah, so our next poll question, and if you guys can just take a moment to answer this by selecting one of the options. Please don't answer in the chat window. We won't get the answer if you do that. But the question is, do you see a need for apps in your activity? So our options are, there is an immediate need, and I would be the app designer. There is an immediate need, and I would be the app user. I foresee a long-term need, or there is no need. So I'm going to give everyone another moment just to finish up answering that. Now I'm going to go ahead and close the poll, and we'll take a moment to look at the results together. So it looks like we have 60% said they see a long-term need, actually, and then 23% said they have no need for it. 12% said there's an immediate need and they would be the designer, and 4% said there's an immediate need and they would be the app user. It's a pretty interesting breakdown there. I'm going to go ahead and close the results, and you can continue, Yusuke.
Sure. Now let's move on to the next TC model. So far, the TC model that we saw was a standalone TC device. What I'm going to show now is a full set of thermoelectric cooling system. The difference from the previous model is that this model has a real heat load and real heat sink that are attached to a TC device. This is a half model all around the symmetry plane here. The heat load is one of the standard 1-inch CS mounted laser diodes having 19 emitters of total 10 millimeter width. This is a laser diode, and this is the emitter part. We don't model individual emitter here. The laser is put on one of the aluminum blocks that sandwich a TC from the cold side. This is the top aluminum block. A TC device is one of the popular size of 40 by 40 square millimeter, having 128 pairs of P and N bismuth telluride elements. This is a TC. The other aluminum block on the hot side, this one, is on the heat sink. The heat sink is this. The heat sink consists of fins with a 2 millimeter thickness and 2 millimeter spacing, and an electric fan modeled by a circular opening at the bottom of the heat sink here. To simulate forced air cooling, we add an air domain occupying fin spacing and extending to some length like this. This is the heat air domain. We also model some thermal resistance between hot side and bottom aluminum block, cold side and top aluminum block, and a laser and the top aluminum block. This is a thermal resistance. In heat transfer, there are some major changes from the previous model. First, we added a radiation condition to our radiating surfaces here. And the ambient temperature is set to be 25 degrees C. And next, we assume the air temperature at the farthest position of the extended air domain here is 25 degrees C as well. And we added a volume heat source for the diode emitter here. We also added a thermal resistance here. The most important change is this one. Remember, we fixed the hot side temperature to 50 degrees C in the previous model. But compared to that, in this model, we no longer impose any temperature or heat flux boundary condition on the hot side of the TC device. Now it's internal boundary and it's automatically set to be floating, which means it's unknown. In this case, the continuity boundary condition is automatically imposed. What do you think determines the hot side temperature? It's a temperature boundary condition set to the outer boundary and radiation condition. This is the key. As we now compute airflow, we added a turbulent flow algebraic Y+ interface. The air inlets are set at the outer boundary again, where the fixed temperature boundary condition was set earlier. The air is exhausted from the circular opening where the electric fan was modeled, and the fan is modeled with a linear static pressure. In meshing, it's a little bit tricky to mesh the space between the fins because the space is narrow, but we need a sufficient number of boundary mesh for accurate computation. In study settings, we compute the wall distance first as we use algebraic y-class. Then it's followed by a stationary study for multiphysics of heat, electric, and flow. Now we take a look at the computational result. This is the domain of full size. The domain is doubled. The parameters that we may be interested in for this model are electric current or voltage applied to the TEC device, or heat load, or thermal paste conductivity, or fan speed. Here I show the results for current sweep. Current is swept from 2 amps to 8 amps with a 2 amp step. This model has about 200,000 elements. It takes about 12 minutes to finish a single parameter run. So I prepared the model file with the solution. So this is the domain. This is the temperature and the flow field. This simulation is with a fixed condition of 20 watt waste heat from the diode, 0.25 watt per Kelvin per meter conductivity for the thermal paste thermal resistance, and the fan's flow rate of 0.025 cubic meter per second. This is also the temperature without the air domain. The temperature, you can see very well TEC part. This is electric potential. This is half model again, and we get about 8 volts. So for a full model, we get the 16 volts. This is the velocity, magnitude, the pressure. And the next one is cross-section of the temperature of center line defined in here. So from the bottom of the TEC to the top of the TEC. So the left half side is hot side, and the right hand side is cold side. And we swept the current from 2 to 8 amps. As you can see, we have temperature difference because we're using the real heat sink, not ideal heat sink. And the gap change varies with the injection current. It's interesting to see that the thermoelectric element works as a material having a negative thermal conductivity. This part is the TEC, so it's like behaving like a negative thermal conductivity. Okay, now we have some jumps and spikes. There are 3 spikes and the jumps here and here. These come from the insulation nature of the thermal paste, thermal resistance. By tweaking this number, you can also model a tiny loss of parallelism of the 2 plates, 2 aluminum plates that sandwich the TEC device. It's worth mentioning that this number affects the performance of the system to a great extent. I'd like to conclude my presentation by one more comment on the last graph, which is the volume average temperature in the diode emitter versus the injection current. We can see from this graph that this TEC system works for the specific diode laser at about a current of 2.2 amp here, assuming the operation temperature of this diode is 25 degrees C. That's all for my presentation. It was a lot of information. I hope you could digest all the information. Thank you. Back to you, Lexi.
Okay, thank you, Yusuke and Nicholas. That was great. It was really good demos you guys did. So it is now time for the Q&A session, and we have a few minutes. We'll answer as many as we can, but we got some really good questions. So I'm going to start with Yusuke. Is it possible to use material properties based on external data?
Yes. You can always import it as a extrapolation data.
Great. Yep. We also got a couple of questions about this app itself. So, Yusuke, why don't you continue with this one? Can you modify this app to create your own app? Can we share the Thermoelectric Cooler app?
Of course, you can.
Okay. Nicholas, why don't you take this one? Is it possible to account for surface-to-surface radiation in my thermoelectric cooler models?
Okay, yes. So that's something that was visible in some of the model we have seen. That we have this diffuse surface boundary condition, which of course can be combined with the other effects. The thermoelectric effects are actually coupled with the heat transfer interface, and all the thing you can model using the heat transfer interface, like surface-to-surface radiation, are available in the multiphysics coupling. That's something which is very, very important and very, very strong in COMSOL Multiphysics. When you couple two interfaces, you get access to all the features of each interface. So if you have been able to do something without thermoelectric coupling, then if you add the thermoelectric coupling, it's still available, and you can benefit from the whole physics interface through the couplings.
Great, thank you. Here's another one for you, Nicholas. Do you need the AC/DC or the CFD modules to run the apps that were shown today?
Okay, yeah, that's that's an interesting question. When you want to implement this model, you need to know which model you have to acquire or for that. So maybe the first thing I should recall is that the thermoelectric effect is part of the heat transfer module. And from that, you can build most of a thermoelectric cooling or thermoelectric effect models you want. But if you want to go far in one direction, for example, if you want advanced electromagnetic effects like floating potential, then you will need AC/DC module. And in the app Yusuke have shown, we are using a port boundary condition, which is part of the AC/DC module. But you could very well find some workaround maybe, and for this particular case, just use the feature that are included in the core of COMSOL Multiphysics, because that's something we haven't discussed today. But when you acquire COMSOL Multiphysics, you get access to the basic physics, and in the basic physics, you have electric current with a couple of features. So you can actually do a thermoelectric effects model just using COMSOL Multiphysics core and the heat transfer module, and you will have access also to the turbulent flow models. But if for some reason you want to add a very advanced flow model, turbulence model, like the SST turbulence model, which is only in the CFD module, then you need it. But if you just want to use algebraic models or K-epsilon turbulence model, for example, then everything is included in the heat transfer module and COMSOL Multiphysics core package.
Great, good answer. All right, we have a question here about, let's see, a question here about hardware. What kind of hardware are you using for this simulation, and what do you recommend? Okay, so the computer we have been using for the demo today, and also for the computational time that Yusuke mentioned, I would say a plain good desktop computer with multiple cores, of course, and some RAM memory, 16 or 32 gigabyte of memory, and that's good to work on this platform. Of course, if you
solve model with more degree of freedom, or you want to gain some time, what we recommend is for workstation, it's good to have a fast processor with multiple cores and fast memory, and the more memory you have, the more degree of freedom you can address, of course. And when it comes to very large model, then it's good to know that COMSOL Multiphysics supports cluster computing, so you can run computation remotely on clusters, and we support a wide range of cluster and operating systems. So I would recommend then, based on your needs, to get in touch with COMSOL and to get a recommendation based on your needs. But the starting point is a good desktop computer with some RAM and some cores to perform the computations.
Great, thank you, Nicholas. Let's see. Yusuke, why don't you take this one? Is it possible to import geometry from another software package, such as a CAD platform, and then kind of work forward defining the materials as it was demonstrated today?
Yes, we support various CAD CAD files. So if you take a look at the CAD geometry mode, then you can see which type of CAD files you can import.
Great. Yeah, we have the LiveLink product shown on the product suite. Okay, let's see. So we actually got a lot of questions about what different kinds of boundary conditions can be used together. So Nicholas, why don't you take this one, and you can maybe expand upon this to other kinds of boundary conditions. But can radiative heat transfer be used with something like periodic boundary conditions or near-field radiative energy transfer?
Okay, so
on that.
Yeah, I guess these are two different questions. So one is about periodic boundary condition with radiative heat transfer. So I guess it refers to surface-to-surface radiation. So for this one, we support a symmetry boundary condition, but we do not support periodic boundary condition. And regarding the near-field radiative energy transfer, there is no built-in support for that yet. So it's not you cannot expect an interface like the one we have seen today, where you just have to fill a few parameters and you get the result. If you want to do that, it will be more based on a user-defined equation or expression to get it to work.
Okay. Great. Actually, that's we had a couple questions about user-defined materials as well and user-defined properties. So, for instance, can you input user-defined thermoelectric material system properties such as silicides, etc.?
Okay, so for the have you seen when you use the predefined implementation of a thermoelectric coupling, you get prompted for some material properties, and we base our implementation on Seebeck coefficient, thermal conductivity, electrical conductivity, and these quantities can be scalar or tensors, and you can define them in almost any way based on external data, interpolation function, analytical expression. And if you have anisotropy, you can also define the orientation of your material based on geometrical property. So it's really flexible, and I guess that's one of the strong points of COMSOL Multiphysics to be very open to user-defined expression or to external data to define. We haven't mentioned, but we have live links also with different softwares like MATLAB, Excel, and if you have data which is not in COMSOL but in this software, and using this the live links, you can access to them and use them in your simulation.
Great, thank you, Nicholas. Unfortunately, that's all the questions we have time for today. We actually got a lot of really good questions, so yeah, we're going to have to move on, unfortunately. But thank you all for your presentation, Nicholas and Yusuke. Thank you all for asking good questions. So we're going to have to go to the next slide. And one question, this is one question that we hear a lot, is how to try COMSOL Multiphysics if you haven't used it before or you want to learn a bit more about it. A really good way to do that is to join us at a workshop. And these are free hands-on events. You can try out the software with the guidance of one of our specialists. You can kind of try it out hands-on, get some help if you need it, ask further questions. You can sign up for these on our website. These are a few of the cities where we, excuse me, these are a few of the cities where we hold workshops, but you can find the full listings on our events page, comsol.com/events. We also recently released the 5.2 version of the COMSOL software, so that's a great thing to download if you haven't yet updated, or if you're looking into what COMSOL can do for you. That's a good thing to investigate. And if you can go ahead to the next slide. This is just some information that you can find on our website. There's more information there about multiphysics, COMSOL, our products. You'll find user stories, our application gallery, and as well as a discussion forum, blog posts. You can contact us a couple different ways. One is through the comsol.com/contact webpage. That's a great way to reach out to us. And please do so if you have further questions. We'd love to hear from you. But that concludes our webinar. So thank you everybody for attending, and thank you Nicholas and Yusuke for your presentation. Have a great day.